Hi everyone, this is Shiying. In this video, I would like to give you a short introduction of mathematical modeling and simulation of the spread of COVID-19. The progress of the epidemic through the population is highly amenable to mathematical modeling, and attempts to model infectious disease actually date back over 100 years. It was the work of Carmack and McKendrick that established the first mathematical theory of infectious disease. They introduced the so-called SIR model, and the model divides the population into the susceptible, infectious, and recovered classes and studies the dynamics between these three groups. We'll see more details later. And there are four learning goals in this video. The first one is to understand the assumptions and dynamics in the SIR model. Secondly, we would like to make sense of an important term called the basic reproduction number R0. Thirdly, we'll show how to use MATLAB to do simple simulation based on the SIR model. And lastly, we would like to emphasize the commonly heard or mentioned term flatten the curve. And in particular, we'll see how the maximum of infectious population is impacted by R0. Now let's start with the SIR model. As mentioned before, the overall population size N is fixed and can be divided into three disjoint classes. The first class is called susceptible class S of T. It is a class of individuals who can incur disease, i.e. susceptible, but not yet infective. The second is called I of T, infection, i.e. the infectious group. It is a class of individuals who are transmitting diseases to others. The third class is called recovered, or some other people call removed class. It is a class of individuals who are removed from the susceptible infective interaction, i.e. they are the class of individuals that once caught the disease but then later recovered or have died. And by assumption, N is equal to the sum of S, I, and R. We should mention that this model has a lot of simplifications compared to real situations. Factors such as natural death or birth are not taken into account. And also, the population is assumed to be well mixed in this model. So let us look at the figure in the middle first. We see that there are two dynamics between the three groups. First is between S and I. And as time goes on, part of the susceptible population will become infected, and part of the infectious population will move to the recovered class either by immunity treatment or by death. So beta represents an effect of contacting between the individuals in S and individuals in I. The first assumption is that the transmission rate per capita, which is ds dt divided by S, is proportional to the infected population, I. So in other words, ds dt will be proportional to S times I. This relation is formalized in equation 1 here. As we see that the change in the susceptible class per unit time will be proportional to the size of the susceptible population and the size of the infectious population. Here, beta over n is just constant. Since beta is a constant and n is a constant, there's a negative sign here since the class of susceptibles is decreasing. The second assumption is that the removing rate is proportional to the infected population I. So dr dt, which is the number of individuals that comes from infectious population to the recovered population, and that should be proportional to the size of the infectious population. This again is formalized in equation 3. Once we have these two relations, the second equation is obvious. The change in the infectious population per unit time is exactly the one that comes from the susceptible class, which is beta times Si over n, minus the ones that are removed from the infectious population, which is exactly gamma I. And to solve this system, we usually have some initial conditions. We assume at time 0, the S0 susceptible individuals and I0 infectious individuals and 0 are recovered individuals. Now, let us give the definition of basic reproduction number. The formal definition is the basic reproduction number is the average number of secondary infections generated by the first infectious individual in a completely susceptible population. Completely susceptible means S0 is approximately the total size n, and R0 is defined to be beta, which is the contact rate between S and I, over gamma, which is the removing rate. So let's first look at the equations and see what R0 indicates. If we look at the equation for the infectious population, we have di dt equals to this term here. If this term is less than 0, means that di dt will be less than 0, means that the size of the infectious population will decrease. And that is a good thing. If we do some algebra, the right-hand side of this equation less than 0 is equivalent to this inequality, i.e. beta over gamma is less than r n over S0. And in a completely susceptible population, this term is approximately 1. In other words, we have shown that if R0 is less than 1, then di dt is less than 0, which means that the number of infected individuals will decrease and disease will possibly not spread. And on the other hand, if R0 is bigger than 1, then the disease will spread. We should mention that in real situations, R0 will not give the whole picture or will not predict precisely how the disease will spread, because the constant beta and gamma will change in terms of the measure that people are taking and the resources that society have at different times. But nevertheless, R0 is a useful term that gives us some nice aspect of the disease. Now let us interpret the term in the definition. So what do we mean by average number of secondary infections? Let us start with beta. So as mentioned before, beta models the contacting effect between S and I. And with Morphos, one can actually show that it represents the average number of individuals that comes into contact with the infected individual. And gamma, which is the proportion of infectious population that are removed per unit time, right? So 1 over gamma is actually the expected infection period. If gamma is large, meaning that per unit time, a large number of infectious individuals are removed, then that shows the average infection period is actually small. So with these two information, we have beta times 1 over gamma, where beta over gamma actually represents the average infections caused by one infected individual during the period when the person is infectious. So if R naught is less than 1, then on average, one infectious person can infect no more than one susceptible individual during the whole period when the person is infectious. And that will show the size of the infectious population will decrease. Okay, now let's come to the simulation part. So here's toy example with n equal to 500, beta equals 0.5, and gamma equals 0.15. And we see that the blue curve, which is the susceptible class, will decrease, and the red curve, which represents the recovered class, which will increase, and the infectious curve will first increase and then decrease to 0. So this is a general trend of the three classes. And let us look at the MATLAB codes for that does the previous simulation. The first step is to set up initial conditions. We set up n equals 500 and x naught, which is the number of S, I, and R at the beginning of the time, which here is 495 susceptible individuals and 5 infectious individuals. And then we set up the time span of the model, which here we start with day 0 and day 80 and end with day 80. The second step is to set up the ODE system. We should give the parameters beta and gamma. Here is gamma is denoted as KR. And then we set up the ODE, where we put the right-hand side of the system of ODE into an anonymous function. We have 3 equations, so actually we have 3 columns. So we write down all the formulas and put into this ODE SIR. And the third step is to use a MATLAB solver, which is called ODE45, to solve the model, where the input is the ODE model and the time span and the initial conditions. It automatically outputs a discrete data time t and a matrix X, when the first column is the susceptible class over the discrete time data t, And the second column of X is the infectious population over the discrete data T, and so on. Now, let us talk about flatten the curve. So this figure here is the curve of number of infectious individuals over time with different beta, where beta ranges from 0.0 to 0.5. And we see that the smaller beta is, the more flat the curve is. And we have another horizontal line representing the capacity of the medical system. So we would like to keep the maximum of infectious individuals known so that the infectious population will not overwhelm the medical system. That is why the officials and the doctors are asking us to practice the so-called social distancing and stay at home as much as possible so that we can lower the contact rate or effective contact rate between the susceptible and the infectious. Again, below there is a code that you can modify and play with different rates, beta, to produce different curves. And that concludes our video. Thank you. Please stay healthy and stay home.